Welcome back to Against the Grain, the channel dedicated to the Mavericks, the rebels, the engineers who were told no, and did it anyway. We love the stories of breakthroughs, of machines that redefine what's possible. We celebrate the Wright brothers, Kelly Johnson, Burt Rutan. But between those famous names lie 1,000 forgotten battles, fought not on the battlefield, but on the drafting board, in the wind tunnel, and in the soul-crushing confines of the briefing room. History is littered with revolutionary ideas that were almost strangled at birth by committees, by experts, by men whose vision was limited by the rule book. Tonight, I'm telling you one of those stories, my story. It's about a time when American air power was hitting a wall, literally. A wall of compressed air that was shaking our best fighters apart, limiting our speed, and giving the enemy an edge. The greatest minds in aeronautics were stumped, throwing millions at solutions that weren't working. And then there was me, a junior engineer, a nobody, with an idea so radical, so counterintuitive, that it wasn't just dismissed, it was laughed at. They called me a joke in that briefing room, patted me on the head, and told me to get back to calculating fuel efficiencies. But that joke, that scribbled drawing born of desperation, it held the key. It was the design that would shatter the wall and redefine the very meaning of speed for American fighter aircraft for decades to come. Before we break the sound barrier on this one, I need you to run your pre-flight checks. First, hit that subscribe button and ring the notification bell. It's the only way to make sure you catch these stories of defiance and innovation. Second, hit that like button. It tells the algorithms that this history matters and needs to be seen. And finally, drop a comment down below. Let us know what country and city you're watching from. It's incredible to see our global audience of aviation and history enthusiasts. All right, pencils down. Let's go make some noise. My name is Richard Whitcomb, and in 1950, I wasn't just a junior engineer at NACA's Langley Aeronautical Laboratory. I was practically invisible. NACA, the National Advisory Committee for Aeronautics, the precursor to NASA, was the high temple of American aviation research. It was populated by giants, brilliant men like Eastman Jacobs and John Stack, men who wrestled with the fundamental forces of lift and drag, men who spoke the arcane language of Reynolds numbers and Mach cones. And then there was me, 29 years old, earnest, maybe a little too intense, armed with a solid engineering degree but lacking the godlike aura of the senior researchers. My official sandbox was the 8-foot high-speed tunnel, a massive, roaring cathedral of wind where we tested models, gathered data, and tried to understand why our beautiful, powerful, swept-wing jet fighters, planes like the F-86 Sabre, were hitting an invisible brick wall as they approached the speed of sound, Mach 1. We called it the sound barrier, but it wasn't a barrier you broke cleanly, like kicking down a door. It was more like wading through molasses that suddenly turned into concrete. As an aircraft approached Mach 1, the air flowing over its surfaces, especially the wings and fuselage, would accelerate, reaching supersonic speeds locally, even when the plane itself was still subsonic. This created shock waves, abrupt, violent changes in air pressure and density. These shock waves dramatically increased drag, sometimes by a factor of 10 or more. They buffeted the control surfaces, making the plane difficult or impossible to control. They could literally shake an aircraft apart. It was the single biggest problem in aviation. Every nation, the Americans, the British, the Soviets, was throwing its best minds and vast resources at trying to punch through that wall cleanly and efficiently. The prevailing wisdom, the gospel according to the giants like Adolf Busemann, whose work we built upon, was simple. Make everything thinner. Thinner wings, thinner fuselages, sharper leading edges. Reduce the cross-sectional area. Make the plane a knife to slice through the air with minimal disturbance. And it worked. To a point. We could get to Mach 1. We could even punch through it, especially in a dive, with enough brute engine power. But the drag penalty was enormous. Going supersonic required colossal, fuel-guzzling engines and resulted in fighters with limited range and maneuverability. The drag rise was a cliff, and we were just barely scrambling over the edge. My job was to run tests, collect data points, and plot the curves that proved this drag rise. Day after day, I'd sit in the control room of the 8-foot tunnel, the roar of the wind a constant, deafening presence, watching the Schlieren imaging, a beautiful, frustrating optical technique that made the shock waves visible as shimmering, ghostly lines wrapping around the model. I saw the drag rise happen hundreds, thousands of times. I saw the shock waves form, strengthen, and choke the airflow, and the thin is better philosophy. It just didn't feel right. We were thinning wings to the point where they were structurally fragile. We were stretching fuselages into long, unstable tubes. We were treating the air like an enemy to be brutally sliced apart. But what if the air wasn't the enemy? What if we could work with it? What if instead of minimizing the disturbance, we could somehow manage it? It was a vague, half-formed thought, the kind of fuzzy intuition that the senior researchers, with their precise equations, would have dismissed instantly. But I couldn't shake it. I started looking at the data differently. Instead of just plotting total drag, I started looking at how the drag was distributed along the length of the model. Where were the shock waves strongest? How did the pressure distribution change as we approached Mach 1? I was looking for a pattern, a clue that everyone else, in their obsession with thinness, might have missed. The epiphany didn't come from a complex equation or a wind tunnel test. It came from looking at the whole aircraft. Everyone else was focused on the wing or the tail or the nose cone, treating them as separate problems. But an airplane flies as a system. The air flowing over the wing interacts with the air flowing over the fuselage. The shock wave from the canopy affects the flow over the tail. It wasn't just about the cross-sectional area of any one part. It was about the total cross-sectional area of the entire aircraft at every point along its length. I started sketching, not sleek futuristic shapes, but graphs. I plotted the cross-sectional area of a typical swept-wing fighter against its length. The graph looked like a series of bumps. A bump for the nose, a bigger bump where the bulky wings attached to the fuselage, another bump for the tail. And right where those bumps occurred, especially the big one where the wings met the body, that's where the drag rise was sharpest in the wind tunnel data. That's where the shock waves were strongest. It was like the air, flowing along the fuselage, suddenly hit the shoulder of the wing, got squeezed, accelerated violently, and tripped into a massive shock wave. What if you could make that progression smoother? What if the total cross-sectional area didn't suddenly jump up where the wings were? What if, as the wings started adding area, you subtracted area from the fuselage? It sounds simple now, obvious even. But in 1950, it was heresy. Aerodynamic design was about smooth, flowing, correct shapes. Intentionally pinching the fuselage, making it narrower where the wings attached, it looked wrong. It looked broken. It violated every aesthetic principle of aircraft design. It looked like a mistake. I drew it anyway. On a piece of standard government-issue graph paper, I sketched a typical fighter fuselage. Then, right where the wings sprouted, I carved out a chunk. I gave it a waist, an indentation, a Coke bottle shape. Some would later call it. My goal was simple: to make the total cross-sectional area graph, the sum of the fuselage and the wings, look like a smoother, more gradual curve instead of a series of abrupt bumps. The theory was that this smoother area progression would weaken the shock waves, delaying and reducing the drag rise near Mach 1. I called it, rather unimaginatively, the area rule. It wasn't based on complex new math. It was based on looking at the existing data in a slightly different way. It was an observation, an intuition, and I knew, with a certainty that made my hands shake, that it was the key. I spent a week refining the calculations, making detailed drawings, preparing my case. This wasn't a napkin sketch. This was a formal proposal. I requested a presentation slot at the weekly aerodynamics research meeting. This was the big leagues. This was where Jacobs, Stack, and the other gods of Langley gathered to review new findings. This was where careers were made, or broken. I knew what they'd think. They'd see the ugly pinched fuselage and laugh. They'd point out that I was intentionally adding wetted area, surface area, which should increase drag. They'd say my theory ignored the complexities of three-dimensional flow. They'd call me a naive junior engineer who didn't understand the fundamentals. And they'd probably be right, according to their own rule book. But I had seen the data. I had seen the shock waves. And I had my graph, my simple, bumpy graph, and my new, smoother one. That was my only weapon. The briefing room at Langley's West area was not designed for comfort. It was designed for intellectual combat. It was a stark, windowless rectangle smelling faintly of stale cigarette smoke and ozone from the projector. The walls were lined with blackboards covered in the elegant, esoteric hieroglyphics of aerodynamic equations. At the front, a heavy wooden table dominated the space, and seated around it were the titans, Eastman Jacobs, whose work on laminar flow airfoils had revolutionized wing design, John Stack, the fiery advocate for supersonic flight who had pushed for the X-1 program, Adolf Bussmann, the German genius whose swept-wing concept was the very foundation of modern high-speed flight, brought over after the war. These were men who didn't just understand aerodynamics, they defined it. And I, Richard Whitcomb, the kid from the 8-foot tunnel, was about to stand before them and tell them they were all looking at the problem the wrong way. My hands were slick with sweat as I set up the slide projector, the clatter of the metal slide holders echoing unnaturally loud in the tense silence. There were maybe 20 people in the room. The senior staff, their section heads, a few other junior researchers like myself, brought in to observe and learn, or, in my case, be ritually sacrificed. I could feel their eyes on me. It wasn't friendly curiosity. It was the collective, critical gaze of experts, waiting to pounce on the slightest flaw, the smallest inconsistency. Mr. Whitcomb. John Stack's voice cut through the silence. He wasn't the head, but he was the most vocal, the most aggressive. The floor is yours. We understand you have some. Thoughts on transonic drag. The way he said thoughts made it sound like delusions. I took a deep breath, walked to the front, and clicked on the first slide. It was simple. A Schlieren photograph of a standard, swept-wing fighter model at Mach 0, 95. The shock waves were clearly visible, thick, angry lines wrapping around the wing root and the canopy. Gentlemen, I began, my voice tighter than I wanted, we are all intimately familiar with the challenge of transonic drag rise. The current approach, primarily focused on minimizing component thickness and maximizing sweep, has yielded significant gains, allowing us to approach and exceed Mach 1. However, the drag penalty remains severe, limiting performance, range, and maneuverability in the critical transonic regime. I clicked to the next slide. It was my graph, the bumpy plot of cross-sectional area versus aircraft length for a typical fighter. Standard analysis focuses on the drag contribution of individual components, the wing, the fuselage, the tail. But the data, particularly the Schlieren imaging and pressure distribution plots, suggest that the most significant drag increase, the most powerful shockwave formation, occurs precisely where these components intersect, specifically at the wing fuselage juncture. I used a wooden pointer, my hand shaking slightly, to indicate the big bump on the graph where the wings added their area to the fuselage. The airflow, already accelerated over the fuselage, is further compressed as it encounters the increasing area of the wing root. This localized rapid acceleration appears to be the primary trigger for the formation of a strong, drag-inducing shockwave that disrupts flow over both the wing and the aft fuselage. So far, so good. I was just stating the obvious, summarizing known data. The giants were impassive, listening, waiting for the hook. Stack was cleaning his glasses. Jacobs was sketching idly on a notepad. Bussmann was staring intently at the screen, his expression unreadable. I clicked again. The next slide showed two area distribution graphs side by side. The bumpy conventional one, and my new smoothed-out ideal curve. My hypothesis, I said, the words feeling enormous, terrifyingly bold, is that the total transonic drag rise is fundamentally linked not just to the cross-sectional area of individual components, but to the smoothness of the longitudinal distribution of the total cross-sectional area of the entire aircraft. I paused, letting that sink in. If we consider the aircraft as a single integrated body, the ideal shape for minimizing wave drag near Mach 1 should approximate a Sears-Hawk body, a theoretically perfect minimum drag shape for supersonic flow, characterized by a smooth, gradual increase and decrease in cross-sectional area. I pointed to my smoothed curve. Achieving this ideal distribution with a conventional wing fuselage arrangement is difficult due to the abrupt area increase at the wing root. I took another breath. This was it. The heresy. I clicked to the final slide. It showed a simple line drawing comparison, a standard fighter fuselage, and my modified, pinched fuselage, the one with the Coke bottle waist. Therefore, I propose a modification to the fuselage geometry itself. By reducing the fuselage cross-sectional area in the region of the wing root, I could feel the collective intake of breath in the room, the sudden, sharp focus of their attention. We can compensate for the area added by the wing, resulting in a total area distribution that more closely approximates the ideal low-drag shape. The silence that followed was not the bored silence from before. It was a stunned, almost offended silence. I had just proposed intentionally making the fuselage uglier, weaker, and seemingly less aerodynamic, based on a theoretical curve derived from supersonic flow principles applied to a transonic problem. It was academic lunacy. John Stack was the first to speak. He wasn't angry, not yet. He sounded genuinely bewildered, like I had just proposed building wings out of cheese. "Mr. Whitcomb," he said slowly, taking off his glasses again, "are you seriously suggesting that we indent the fuselage? That we intentionally create a concave shape on a body designed for external flow?" "Yes, sir," I said, trying to keep my voice steady. "To smooth the overall area progression. But, good God, man, that increases the wetted area," Stack exclaimed, his voice rising. "You're adding surface area right in the region of highest flow velocity. Basic boundary layer theory dictates that will increase skin friction drag. You're trading a potential reduction in wave drag, which is purely theoretical at this point, for a guaranteed increase in friction drag." Eastman Jacobs nodded in agreement, finally looking up from his notepad. "The boy has a point, John. The friction drag penalty could easily negate any wave drag benefit, especially at lower transonic speeds." "And the structure," Stack continued, warming to his theme. "You're proposing carving a massive chunk out of the most highly stressed part of the fuselage structure, right where the wing spars attach. The weight penalty required to reinforce that indented section would be enormous. You'd add hundreds, maybe thousands of pounds, negating any potential drag reduction simply through increased mass. Furthermore," a new voice chimed in, smooth, precise, and tinged with a German accent. It was Boosman. He stood up and walked slowly to the front, pointing at my pinched fuselage drawing. "Your area rule, as you call it. It is an interesting observation about the Sears-Hawk body, which applies to slender bodies in supersonic flow. But transonic flow is fundamentally different. It is a mixed subsonic-supersonic regime. The shock waves are localized, complex, and highly dependent on the local geometry, not just the overall area distribution. Indenting the fuselage here," he tapped the drawing, "could create adverse pressure gradients, leading to flow separation, buffet, instability. Potentially increasing drag, not decreasing it. You are applying a supersonic principle too simplistically to a much more complex transonic reality." He was dismantling my entire premise with surgical precision, using the very theories I had used to build it. I felt my face flush hot. He was right. Or rather, he was right, theoretically. But I had seen the data. "Sirs," I managed to say, my voice embarrassingly shaky, "I understand the concerns about friction drag, structural weight, and flow separation. But the wind tunnel data, the pressure plots, they consistently show the dominant drag component near Mach 1 is wave drag, originating precisely at that wing fuselage juncture. If we can significantly reduce that primary shock wave, even at the cost of a small increase in friction drag or structural complexity, the net effect should be a substantial reduction in total drag right where we need it most, in that transonic wall." "Should be?" Stack scoffed. "Mr. Whitcomb, we don't design multi-million-dollar experimental aircraft based on should be. We base it on proven aerodynamic principles and rigorous calculation. And your calculations," he waved dismissively at my slides, are based on a gross oversimplification, applying a one-dimensional rule to a three-dimensional problem. It's academically unsound. It's worse than unsound, another voice barked from the back. It was Robert Jones, another brilliant theorist, known for his work on delta wings. It's ugly. It violates the fundamental principle of aerodynamic smoothness. You're intentionally creating discontinuities. It's aesthetically offensive. That was when the laughter started. Not loud, but a low, rumbling chuckle that spread through the room. They weren't just refuting my theory, they were mocking it. The area rule wasn't just wrong, it was ugly. It was offensive to their finely honed sense of aerodynamic beauty, their belief in smooth, perfect, mathematically derived shapes. My pinched fuselage was a monstrosity, a violation of their faith. I stood there, frozen, pointer still in my hand, the laughter washing over me like ice water. I had failed. I had presented my heresy to the high priests, and they had not just rejected it. They had declared it a joke. "Thank you, Mr. Whitcomb," Stack said, his voice laced with finality and pity. That was stimulating. Perhaps you should focus your talents back on the efficiency data from the 8-foot tunnel. Clearly, transonic theory is not your forte. Dismissed. I gathered my slides, my hands numb, my face burning. The room was already moving on. Someone else starting their presentation on boundary layer control. I walked out of that room, the sound of their casual, dismissive laughter echoing in the hallway. They had called me a joke. They had killed my idea. Or so they thought. But they hadn't seen all my data. They hadn't seen the secret, unauthorized tests I'd run, late at night, using a crude, hand-carved wooden model with a fuselage shaped like a Coke bottle. And they hadn't seen the numbers from that test. Numbers that showed a drag reduction not of 5%, not of 10%, but of 25%. Numbers that proved my ugly, broken joke of an idea was the key to shattering the sound barrier. The briefing room had rejected me. Fine. The wine tunnel hadn't. Walking out of that briefing room wasn't a walk of shame. It was a walk of cold, hard, furious certainty. The laughter echoed, yes, but it wasn't the sound of defeat. It was the sound of ignorance. It was the sound of men so blinded by their own established brilliance, so comfortable in their theoretical castles, that they couldn't see the simple, ugly truth staring them in the face. They had laughed at my pinched fuselage, my Coke bottle, my violation of aerodynamic aesthetics. They had nitpicked the theory, citing friction drag, structural complexity, flow separation, all valid points in their perfect, theoretical world. But they had ignored the elephant in the wind tunnel, the massive, crippling wave drag that was the real enemy. My crude, hand-carved, wooden model, tested in the dead of night when the official programs were shut down, using bootleg tunnel time begged from a sympathetic technician who owed me a favor. That model hadn't lied. The numbers on the manometer board, photographed with my own Kodak Brownie camera before I frantically erased the evidence, hadn't been a hallucination. A 25% reduction in transonic drag, not 5%, not 10, 25. It was a number so large, so impossible according to their theories, that I almost hadn't believed it myself. But the data was undeniable. My ugly, broken, academically unsound joke worked. And it worked spectacularly. But what could I do? I was Richard Whitcomb, the invisible junior analyst. I had presented my heresy to the high priests, and they had excommunicated me. To push further, to wave my secret, unauthorized data in their faces, would be professional suicide. They wouldn't just fire me. They'd likely try to prosecute me for misuse of government facilities, for falsifying test logs, which I technically had done to cover my tracks. My career, my dream of contributing to the cutting edge of aeronautics, would be over before it truly began. I was trapped. I had the key to unlocking supersonic flight, a key that could redefine American air power, ensure our edge over the Soviets, save pilots' lives. And I couldn't tell anyone. The frustration was a physical ache, a constant burning knot in my stomach. I went back to my official duties in the 8-foot tunnel, running the endless, tedious tests on wing configurations and tail designs for programs I now knew were fundamentally flawed. I watched them struggle, watched them hit the same drag wall again and again, watched them celebrate a minuscule 2% drag reduction achieved by shaving another millimeter off a wing's thickness, knowing that my ugly Coke bottle could give them 10 times that improvement. It was maddening. I felt like Cassandra, cursed with the knowledge of the future, but unable to convince anyone to listen. My work became my refuge, but also my secret laboratory. I couldn't build more models. The risk was too great. But I could think. I could refine the theory. Boosman's critique had stung the most because it held a kernel of truth. Applying a simple, one-dimensional rule, overall area distribution, to a complex three-dimensional flow field was an oversimplification. Why did it work so well then? I spent months in my spare time diving deeper into the math, into the still emerging theories of transonic flow. I wasn't just thinking about the total area anymore, I was thinking about the rate of change of that area. The bumps on my original graph weren't just bumps, they represented rapid changes in the area progression, forcing the air to accelerate and decelerate violently, triggering the shock waves. My pinched fuselage wasn't just reducing the area at the wing root, it was smoothing the transition. It was easing the air's journey past the bulky wing intersection. It was like designing a smoother on-ramp for a highway, preventing the traffic jam, the shock wave, from forming in the first place. I started to develop a more refined mathematical model, one that accounted for the three-dimensional interactions, predicting not just that the area rule worked, but why and how much. I filled notebooks with equations, sketching modifications, considering different fuselage shapes, different wing positions. I realized the indentation didn't have to be a simple pinch. It could be tailored, sculpted, optimized for specific wing shapes and Mach numbers. The area rule wasn't just a single trick, it was a design philosophy. All this work was done in secret, late at night in my small apartment, the blinds drawn, the notebooks hidden under my mattress. I was becoming a ghost in the machine at Langley, quiet, diligent, but detached. My colleagues noticed the change. The initial jokes about my Coke bottle presentation faded, replaced by a cautious distance. I was the guy who had challenged the gods and been struck down. I was marked. My career prospects at NACA looked bleak. I considered leaving, taking a job in the private sector, maybe at Boeing or Lockheed. But the problem wouldn't let me go. Every time I read a report about a new fighter prototype struggling with transonic drag, every time I heard rumors of another test pilot killed pushing the envelope, the fire in my gut would reignite. My joke wasn't a joke, it was the answer, and it was sitting uselessly in my hidden notebooks. The break came, as it often does, not from within my own world, but from the outside. The United States Air Force was in trouble, big trouble. Their next-generation interceptor, the Convair F-102 Delta Dagger, the plane designed to stop Soviet bombers cold, was a disaster. It was supposed to be supersonic in level flight. It had to be, but it wasn't. It couldn't break Mach 1. No matter how much engine power they threw at it, and they were throwing everything at it, it would hit Mach 0, 98 and just stick. The drag rise was a vertical cliff. Millions of dollars, national security, the entire interceptor strategy. All were grinding to a halt against the same invisible wall I had been studying. Convair's engineers were desperate. The Air Force was furious. Langley, as the nation's premier aeronautical research center, was under immense pressure to find a solution. Any solution. And all the thin wing, sharp nose, conventional fixes weren't working. John Stack, the man who had dismissed my area rule as academically unsound, was now neck-deep in the F-102 crisis. He was a brilliant, pragmatic man, and despite his initial skepticism, he was also desperate. The official approaches had failed. Rumors, whispers of my secret, unauthorized wind tunnel results must have reached him, perhaps through the sympathetic technician who had helped me. Or perhaps, staring at the F-102's intractable drag data, he remembered my presentation, my graph, my ridiculous pinched fuselage, and thought, what if? What if the kid wasn't entirely crazy? What if that 25% number, even if obtained through unorthodox methods, held a grain of truth? Desperation is the mother of invention, and sometimes it's also the mother of second chances. I received a summons. Not a formal letter, not a meeting request. Just a scrawled note, delivered by hand. Whitcomb, my office, now. Stack. My blood ran cold. This was it, the reckoning. Had he found out about my hidden notebooks? About my continued insubordinate research? I walked to his office, my steps heavy, bracing for the final, career-ending blow. Stack's office was surprisingly cluttered, overflowing with models, reports, and half-smoked cigars. He didn't waste time on pleasantries. He threw a thick binder onto his desk. F-102 drag data, he grunted. It's a pig. We've tried everything. Thinner leading edges, vortex generators, boundary layer fences. Nothing touches that drag rise. He looked up at me, his eyes sharp, appraising. Your presentation. The one about the fuselage indentation. The area rule. I just nodded, my throat dry. You had some data, didn't you? Wind tunnel data, showing a significant drag reduction. I hesitated. Admitting to unauthorized tests was a confession. Sir, the data was preliminary, unofficial. Damn it, Whitcomb. Don't play games with me. Stack slammed his hand on the desk. The Air Force is breathing down my neck. Convair is about to lose the contract. Did your ridiculous Coke bottle work or not? This was the moment. The gamble. Yes, sir, I said, my voice quiet but firm. It worked. My unofficial tests showed a drag reduction of approximately 25% at Mach 0. 98. Stack stared at me, his eyes wide. 20. 5. He ran a hand through his already messy hair. Jesus Christ. 25%. He was silent for a long moment, the implications sinking in. A 25% reduction would blow the F-102 straight through the sound barrier. Okay, Whitcomb, he said finally, his voice low, conspiratorial. Here's the deal. Officially, your area rule is still nonsense. Officially, you are still the junior analyst from the 8-foot tunnel. But, unofficially, you have access to the 16-foot tunnel. You have a budget, small, discretionary, invisible. You will build a proper model, an F-102 model, incorporating your fuselage modification. You will test it, properly, with official instrumentation, and you will bring me the data. Quietly. If it works. He paused. If it works, we'll figure out how to tell the world you were right all along. If it doesn't work, this conversation never happened. You never built a model. And you will be calculating fuel efficiencies in Alaska. Understand? I understood. It wasn't vindication. It wasn't an apology. It was a desperate, high-stakes, off-the-books gamble. But it was a chance. My joke was about to get its day in court. The 16-foot transonic tunnel was a different beast entirely. It was the crown jewel of Langley, capable of speeds up to Mach 1. One with instrumentation far more sophisticated than the old 8-foot rig. This wasn't bootleg time. This was stack-running interference, pulling strings, creating a pocket universe where my heresy could be rigorously, scientifically tested. We worked with a feverish intensity. My small, hand-picked team, including the technician who'd helped me with the first secret tests, Stack had promoted him. We took Convair's official F-102 model, a beautiful, precise metal thing, and we committed butchery. We didn't just add a pinch. We re-sculpted the fuselage based on the refined area rule calculations I'd developed in my notebooks. We carved out sections near the wing root, subtly bulged others near the tail cone, creating a smooth, flowing, organic shape that followed the ideal area progression curve. To the untrained eye, the changes were almost invisible. A slight narrowing here, a gentle swelling there. But aerodynamically, it was a revolution. The modified model, sitting in the stark light of the tunnel's test section, looked Right. It no longer looked like separate pieces bolted together. It looked like a single, unified, purposeful shape, sculpted by the very air it was meant to conquer. The day of the official test run was nerve-wracking. Stack was there, pacing behind the control console, chewing on an unlit cigar. A contingent from Convair, looking grim and skeptical, watched from the observation window. The Air Force liaison officer, a full colonel, tapped his foot impatiently. The tunnel spooled up, the familiar roar building, the air beginning to scream past the model. We started the run, Mach 0, 8, 0, 85, 0, 9. The drag numbers, displayed in real time on the cathode ray tubes, were tracking normally, matching the baseline data from the original F-102. Then, Mach 0, 95, 0, 96, 0, 97. This was the cliff. This was where the original design's drag coefficient skyrocketed, where the shock waves bloomed, where the plane hit the wall. On the screen, the drag line just kept going. It didn't jump. It didn't spike. It continued its smooth, gentle upward curve. Mach 098, the F-102's previous limit, sailed by. Mach 0, 99, Mach 1, 0, Mach 1, 2. The model was supersonic. And the drag was 60% lower than the original configuration at Mach 1. 60%. It wasn't just a reduction, it was an annihilation of the problem. The room was silent. Stack stopped pacing. The Convair engineers were pressed against the glass, their mouths open. The colonel just stared at the numbers, shaking his head slowly in disbelief. My ugly, broken, academically unsound joke of an idea had just blown the doors off the sound barrier. The rest, as they say, is history. The area rule wasn't just applied to the F-102. It saved it. Convair, in a desperate, unprecedented move, took F-102s that were already on the production line and physically cut them apart, inserting new, area-ruled fuselage sections to create the characteristic WASP waist. The redesigned F-102A Delta Dagger easily exceeded Mach 1 in level flight and became the backbone of America's air defense for years. But the impact was far greater than one aircraft. The area rule wasn't just a fix, it was a fundamental revelation. It instantly became a core principle of high-speed aircraft design, applied to virtually every transonic and supersonic aircraft developed since, from the F-106 and F-4 Phantom to the B-58 Hustler, the Concorde SST, and even modern fighters like the F-22 and F-35. That simple concept, smoothing the total cross-sectional area distribution, became one of the most significant and enduring breakthroughs in the history of aerodynamics. My joke redefined U.S. fighter speed, and indeed, the speed of aircraft worldwide. I received the Collier Trophy, aviation's highest honor, in 1955. The citation didn't mention the laughter, the rejection, or the secret tests. It just praised the revolutionary concept. But I knew, and Salty knew. Stack made sure he got a promotion too. And Stack knew. The men who had laughed in that briefing room. They eventually came around, some grudgingly, some enthusiastically. Science, unlike dogma, eventually yields to data. My name is Richard Whitcomb. They called me a joke. But my design, born on graph paper and validated by a crude wooden model, proved that sometimes the most elegant solution isn't the prettiest one. Sometimes, to go faster, you first have to embrace the ugly.